Okay, so again, take a situation, mass m1, mass m2, velocities v1 and v2, they collide, the balls hit, they're going to hit off center, most likely, not head on, although they could, but they come off with velocities u1, excuse me, and u2. And we want to analyze the force, okay, the force of interaction. Okay, again, assume an isolated system. And just to remind ourselves, that means that F12 equals negative F21, and these are net forces. Now let's say that the collision lasts time delta t, that is the duration of the collision, is delta t. And now let's get some numbers in these things. Let's let m1 be 2 kilograms. Now let's see, looking at this, which of these is going to be more massive? That gets knocked off there, that gets knocked off there. So I'm going to say M2 is 3 kilograms. I'm going to say that V1, now it's got an angle. Okay, so it's going to have an I and a J component. Now I could give it to you as a speed and an angle with some axis. Okay, and then you'd have to use a sine and cosine to find the components, but I'm going to assume everybody knows how to do this at this point. So V1 is going to be, let's say, 4 meters per second times the I vector plus 2 meters per second times the J vector, the greater I component than a J component. V2, on the other hand, has a greater J component than an I component, and its I component is going to be negative if this one's positive, if we're assuming a horizontal x-axis. So V2 equals, I don't know, let's say, it's more massive, it's moving faster, so that component looks like it would be about 6 meters per second. Well, that'd be the J component. So we're going to say negative 2 meters per second times I plus 6 meters per second times J. Okay, and delta T, now I don't know, if we don't make these steel balls, then the duration of the collision is going to be pretty low. It's going to happen very quickly, just probably a fraction of a millisecond. If it's pool balls, they give a little bit more than steel, so the collision's going to last a little bit longer, and it'll probably be at least a few milliseconds, maybe several milliseconds. So let's just say that delta T equals 7 milliseconds. 0.007 seconds. Okay, our ultimate goal then is to get the force. Well, to get the force, oh yeah, and let's say that let's say we know U1 to be if that ball's more massive than that one's not going to go off in that direction. If this one goes off in this direction, I'm going to say this thing goes off like so. And total kinetic energy should be conserved. This vector should be a little shorter than this one, so I'm going to make this one a little longer. Okay. I say total momentum should be conserved. Anyhow, okay, U1, we're going to say is maybe negative 3 meters per second times I plus 2 meters per second times J. Now a minute ago, I'm going to change the wrong camera because walking over to the video camera, what I need to adjust is the camera of the laptop so you can see all this. Okay, so we have all this information. Now we automatically know that momentum is conserved. It's an isolated system, just these two masses. So we could write this out very easily, just using impulse momentum, but we might as well use this funky equation up here. So we can say that M1, well, let's write out the equation, M1 V1 plus M2 V2 equals M1 U1 plus M2 U2. Now, V1, V2, U1, and U2 are going to be vectors with I and J components. We need a little bit of room here, but I'll probably do it in 2 lines. So we're going to have M1 multiplied by, well, M1. Okay, we know what M1 is. Actually, let's solve this symbolically. I don't want to clutter things up too badly. So the only thing we don't know is U2. We know M1, we know M2, we know V1, we know V2, and we know U1. So U2 is going to equal M1 V1 plus M2 V2 minus M1 U1, all divided by M2. Well, that's really pretty easy now. All we've got to do is substitute our masses and our velocities, and we're going to get U2. Give us a little more room here. Okay, so this equals 2 kilograms times 4 meters per second I plus 2 meters per second J. Now your book tells you just check out the units and then just write the numbers. I'm not going to do that. I understand what they're doing and why they're doing it, but my experience is people screwed up when you let them gloss over the units. So I'm going to be pretty rigorous about the units. Okay, and then it's going to be, okay, that's your M1 V1 here. Your M2 V2 is going to be 3 kilograms times V2, which was negative 2 meters per second, I, plus 6 meters per second J. And I'm going to continue with the numerator here, and it's going to be minus, not plus, minus M1 U1, which is 2 kilograms, times negative 3 meters per second times I, plus 2 meters per second times J. And that's all going to be over M2, which is 3 kilograms. Okay, well, we want to separate out the I and the J components. So we get 8 kilogram meters per second times I from this. And then we're going to get negative 6 kilogram meters per second times J from this. And from here, we're going to get plus 6 and this is I, not J, okay? And then that's going to be plus 8 plus 4 kilogram meters per second times I here. Over here we're going to get 18. That's times J. You see why I can't work through these things anymore. Just careless. Okay, that's J. Okay. See if we can get this one right. Plus 18 kilogram meters per second times J. And then minus 4. Kilogram meters per second times J, all divided by 3 kilograms. Well, the I's add up to 8 kilogram meters per second because these two happen to be equal and opposite. I hate the word cancel. People will cancel a 6 over here with a 6 over there in the next room if you give them a chance. And it's an epidemic. Even engineers do it. Okay, want to make sure you're using the rules. Just my opinion. So we have 8 kilogram meters per second times I plus what? 4, 22 minus 4 is 18. Kilogram meters per second times J, all over 3 kilograms. Which equals then 8/3, and I don't want to go to decimal here, although in real life you kind of do, because these are real quantities. They're not measured with 100% precision anyway. But I'm going to be a purist here. So it's 8/3 of a meter per second times I plus 6 meters per second times J. Now this means that when I said U2 is going off in this direction, I lied, I was wrong. It's actually going to go off kind of in this direction because this is almost twice as much as this. Matter of fact, it's a little more than twice as much as this. So your J component's a little more than twice your I component, and your speed is probably a little more than what I've said there. Okay, it's going to go off like so. So let's just go ahead and correct that. So, okay, it actually goes off like this. Kind of a glancing collision. Okay, there we have it. If I've done all this right, that's the way it works out. I'm thinking that maybe something isn't quite right here because it looks to me like I might possibly have more kinetic energy after the collision than I had before the collision. But that's just because of an assumption I made. So you can't have more kinetic energy after collision than you have before collision if you simply have Newton's third law interaction. That says, is there a kinetic energy violation here? Something you kind of always want to think about. If you do an actual experiment and you end up with more kinetic energy afterwards than you had before, and there's no source of potential energy in the interaction between these two things, then you know something's wrong. Okay, so, but for this case of this, for the sake of this problem, it doesn't really matter, but I think it might be unrealistic. Okay, now we want to get the net force. Well, okay, so let's say that what's delta P1? Now actually, we had enough information to calculate the net force based on the 7 millisecond interaction. Since we knew the velocity of m1 before and after, so we could calculate the change in momentum of the first mass and divide that by the time interval to get the force. Okay, so delta P1 is what? It's the momentum of the first, which is 8 kilogram meters per second times I plus 4 kilogram meters per second times J, subtracted from its momentum after the collision, which is here 6 kilogram meters per second times I minus 4 kilogram meters per second times J. So it's M1 you want to write it M1, got everything wrong there, M1 U1 minus M1 V1. Okay, M1 V1, the momentum before, M1 U1, the momentum after. It'll be this minus this, and of course I can factor the M1 out of that. Now if I wanted to calculate the force, I could go ahead and put my delta T down here. And I'd put my delta T down here, and I'd get the force. I'm going to calculate the change in momentum, and then I'm going to calculate the force. For no good reason particularly. If you're trying to be efficient, you probably want to combine things, and you gain insight doing that. But I'm going to do it this way anyway, because we're going to look at one concept at a time. Okay, so delta P1 equals this, which is easy enough to find a place where this chalk writes correctly. So your M1U1 is 6 kilogram meters per second times I minus 4 kilogram meters per second times J. Minus M1V1, which is 8 kilogram meters per second I. That 8 came out kind of small, might be hard to read. And then plus 4 kilogram meters per second times J, which is going to be then negative 2 kilogram meters per second times I. Yeah, that's right. Minus 8 kilogram meters per second times J. So, one concept, there's your change in momentum. Another concept then, this force exerted on the first object by the second. And I'm not sure I got my subscripts right there, but I'm not going to worry too much about that, is delta P1 over delta T, which is negative 2 kilogram meters per second I minus 8 kilogram meters per second times J divided by 0.007 seconds. And that comes out, well, let's see, it'll be about 140 times this. It's going to come out about negative 280. It's ballpark, it's a little more than that, but negative, or the number's a little bigger than that. Negative 280, and it's going to be kilogram meters per second divided by seconds, which is kilogram meters per second times reciprocal seconds, which is kilogram meters per second squared times I. And then 140 times that's going to be 1,080. Is that right? 800 and 280. Yep. Minus 1,080. Kilogram meters per second squared times J, which is then, of course, negative 280 newtons times I minus 1,080 newtons times J. Now we could get the magnitude and angle. Now we can find the magnitude and the direction. We just use the arctangent to get the direction with respect to the horizontal. Since the I component is negative, we're going to have to add 180 degrees to the arctangent. And we use the Pythagorean theorem to find the magnitude, and there we've got it, if we're asked for that. And we see that the magnitude of this force is probably around maybe 1,200 newtons. And that would be a fairly typical force if these were maybe somewhat more massive pool balls. At those velocities, I would think the force might even be more than that. The interaction time might be somewhat less than 7 milliseconds. So maybe they're soft pool balls, I don't know. Okay, anyhow, there we have it. Maybe you don't want the pool balls to collide at these velocities because they're big and their strength to mass ratio or strength to momentum ratio is higher than it would be, lower than it would be for a small pool ball. And I'm just raving now and speculating. So maybe you want to put a little bit of a plastic surface on them or something to spread out the interaction, spread out the force, give you a smaller force. That's worth thinking about.